Chip on into part 2 here. So far we've drawn our picture. That's step 1. We have written out all of our given values, step 2. Now what we're going to do is we're going to look at our kinematic equation. So step 1, step 2, step 3. Our kinematic equations are here. Now, when we are using these, if it is a vector quantity, we have to be all in the x or all in the y when we plug it in. Meaning if my v final is the x, my v final, my v initial, my acceleration, my delta x, my delta y, or my acceleration all needs to be in the x. If it's in the y, it all needs to be in the y. So let's look. In my x values, I have 3, and my y I only have 2. So odds are my x is where I'm going to start here. I know I'm looking for something in the y, but there's something we can find in the x that we can then use in the y. And if we think about it logically, if I know it's going to do this, like it's going to come over here and it's going to drop a bit, I don't know v final, I don't know delta y, and I don't know time in the y. So that means I got to find something else. So what I can do is, because I do know delta x, and I do know v initial, and I know the acceleration of x is 0, I can find time in the x. And then I can say, well, if it hits here in the x, it also hits here in the y. So that's why time being a scalar quantity is a really good bridge for us to get between the two of them. And it is scalar, so it is the same in both. Okay, so I'm going to look at my equations here and see which one of them can help me find time. I don't have v final, so I can't use that one. Don't have v final. V initial times time plus 1/2 times acceleration. Well, acceleration is 0, so that falls off. So I don't actually have to use a quadratic, thank goodness. And I can say my delta x is equal to this, so that looks perfect. So I'm going to use equation number 3 here in the x and say that my v initial in the x times time, I should say is equal to delta x first of all. I'm going to rewrite that. Okay, so delta x is equal to v initial times time plus 1/2 at squared. Because acceleration is 0, this entire part becomes 0, so plus 0 falls off. And I have my delta x is equal to v initial times time. I have delta x up here, and I have my v initial up here, so I can plug and chug now. My delta x is 180 meters. My v initial is 800 meters per second times time. Now to get time by itself, I'm going to divide, because it's multiplication, by meters per second. So that crosses off, and times by itself divided by 800 meters per second. Meters divided by meters cross off, and 1/1/seconds gives me a unit of seconds, and that's a good dimensional analysis check that my algebra was correct. Now 180 divided by 800 to 3 sig figs gives me 2.25 times 10 to the negative first seconds. Now that time I can use over on the y side and find my delta y, because now that I know how long it was in the air, I can figure out how far it dropped. Because you either need a v final to know how long it was up, or you need a time to know how long the acceleration was impacting it. So now let's look at the kinematics again. If v initial is 0, I'm jumping to this one because these have v final in it, and I don't have v final. I don't have to look for it. You could, but it's just an extra step you don't need to do. So instead of delta x, I'll say delta y. My v initial is 0, so that falls off. And I get that. So we're going to do equation number 3 again. So we're going to say delta y instead of delta x, just because it's in the y direction. V initial in the y times time plus 1/2 e in the y t squared. All right, time is, it's going to be a 0, and time is squared. That's the number one mistake here I see. Delta y is what we're solving for. 1/2 negative 9.81 meters per second squared times time squared, so times 2.25 times 10 to the negative first seconds squared. Notice that unit becomes seconds squared, and seconds squared times meters per second squared means that crosses off. I'm left with meters, which is my unit for delta y, so unit checks out. And I still have this on my calculator, so I'm going to square it. And I'm going to take it times negative 9.81 times 0.5. I am getting a negative 2.48 times 10 to the negative first meters, which they said 250. Yeah, they must have been sig fig slightly different. And it says how far does it fall, so that's why that's a negative. It's the delta y as a vector quantity is negative, but if they said how far does it fall, you can say it as a positive if you'd like. But knowing that obviously delta y is a negative value. All right, that was number 1.